So for section 5.1, we're going to start looking at rational functions and their graphs. So I have kind of the PowerPoint I'm going to try to follow, but as I go through the notes, I'll just switch to this. So what is let's see, 5.1. What is a rational function? Well, ratio basically means fractions. So this is where I have the equation as a fraction. Ratio means we're going to have a fraction, okay? We're going to have two different restrictions on this. So we will have a asymptote on the x, also known as a vertical. I'll learn how to spell here. And we get this because we have a fraction. There are certain values that we cannot divide by, right? So whatever the denominator is, whatever that denominator is, it cannot equal 0. So whatever is down there as the g of x, whatever on the bottom, cannot be 0. That gives us our restriction on x. Whatever's down there, we solve for what makes it 0, and that's a restriction. As far as the y asymptote, because this will have both, there's going to be two ways, and this will be our horizontal asymptote. There's going to be two ways to see this. We can see it with like a horizontal shift and a vertical shift, so almost like an H and a K. Okay, but what I'm going to do is I'm going to teach this as thinking about what happens as x gets really big, as x approaches infinity, or as x approaches negative infinity. What happens is y will approach some value, never equal that value, but it'll get really close. And so y will not equal. Okay. So what we'll do is we'll kind of start with what we already know. One of the easiest rational functions would be if we just had 1 over x. Okay. What does 1 over x look like? And this will be kind of our parent graph. Well, if you don't know, then you plug in points. So we say, well, what if x were 1? What if x were 2? What if x were 3? So on. Well, if x were 1, 1 divided by 1 would be 1. If x were 2, 1 divided by 2 would be 1/2, 1/3, 1/4, 1/5. What happens? Well, this is getting closer and closer to 0. We've seen this before. What happens when it's negative? Well, 1 divided by -1 is -1. Then -1/2, then -1/3, 1/4. What this does is it helps us see our horizontal asymptote. Our horizontal asymptote here, y cannot equal 0. What about the vertical asymptote? Well, that comes from the denominator. Okay, so y cannot equal 0. That's our horizontal asymptote. Our vertical would be take whatever's in the denominator and say it cannot equal 0. Nothing to solve here. X can't equal 0. That's a vertical line at 0. And that would be our vertical asymptote. So what happens kind of in this region right here where we're dividing by really small things? So if I divide by small things, the values get bigger. For instance, if I took 1 and I divided it by 1/2, I got 2. So that would be 1/2 goes all the way up to 2. What happens if I divide it by something smaller? Like 1/10. Well, that jumped all the way up to 10. So this jumps all the way up to 10. So what this graph does is it rockets upward but never reaches. That's our definition of a asymptote. So that's why our asymptote for the vertical is that x cannot equal 0. Well, the graph is going to get closer to that but never reach it. What about on the negative side? Well, same thing. Negative 1/2 makes it negative 2. Negative 1/10 makes it negative 10. This skyrockets the other way. Okay? So this is our parent graph, and what we can do is we can build all our other graphs off of this one. We're going to have a lot of different, but basically our standard form is going to be y is equal to a over x minus h plus k, where what? H is the horizontal shift, k is the vertical shift. And really, if you look at our parent graph, both of these asymptotes were at 0. So that h and that k actually create our asymptotes. The horizontal shift at h basically says that x cannot equal h. That would be our vertical asymptote. And the k is this horizontal line, be our horizontal asymptote. That would be right here. Y cannot equal k. I like the not equal. A lot of books won't do that. I know in the homework they won't do it, but I like to think about it because it's really what y can't equal and what x can't equal. Okay, so that's kind of a quick intro to this, and now we're going to graph some more complicated examples from this. Before I move on past the parent graph, I just want to make sure we still can state our domain and range. And there are a couple ways of doing this. They're going to want interval notation, but our domain is basically saying x can equal anything, is all real numbers, right? Except x cannot equal, well, 0 in this one, but it'll be the, make sure I get this right, the horizontal shift. The way I would write that on this one is that x goes left forever, right forever, but it has a hole right in the middle at 0. So it goes from negative infinity to 0, and then it has a hole there from 0 to infinity. So this right here shows that x cannot equal 0. It's anything to the left, anything to the right, but not 0. The range will be the same thing. It'll be all y values that are real, except what? Well, y will not be able to equal k, the vertical shift. So in this one again, y cannot equal 0. So how would I write that as an interval? Negative infinity to 0, or 0 to infinity. So they are going to bring up domain and range again. Don't let that get away from you. So let's glance through here real quick. So this was just talking about the 1 over x, the domain, and the range. Vertical asymptote, horizontal asymptote. They talk about using the technology. Feel free, but I would expect you to be able to graph these by hand. So this was what? 1 over x. Our horizontal asymptote at 0, our vertical at 0, fits what we said, okay? Now what if we played with this a little bit? What if I put negative 2 over x? Well, let's see. Well, there's a couple things we could do right off the bat, right? This has now an a of negative 2. That will stretch the graph, so it'll make it twice as tall, and the negative means that it will be reflected. So if I know what the parent graph looks like, all this one is going to do is basically flip it twice as tall, and reflected. But beyond that, it's the same graph and has the same asymptotes as its parent graph. Okay, so I can show that again on my calculator. If I made that -2 over x, this will look just like the parent, but what? Reflected and twice as tall. So instead of going to 1, it goes to -2. Instead of 1/2, it goes to 1. It's twice as tall, and it's reflected. What if I made it 2 over x plus 1? Well, depending on, again, I know what this looks like. It's going to be, a is a 2, so it's going to be stretched by a factor of 2, but this time it's not reflected, since the a is still positive. Okay? But what is this 1? Well, that is our h. What is our k, right? It's supposed to be plus k. Well, our k, since there's nothing there, is equal to 0. So if I know what the parent graph looks like, what this one does is it shifts it -1 horizontally. The shift is opposite. So x cannot equal -1. If you didn't see that, you could take the denominator, x plus 1, and say it cannot equal 0. Solving for x, we say x cannot equal -1. So that is our horizontal shift, back 1. Our vertical shift, so this would be our vertical asymptote. Okay, there is no shift, so y will stay at 0. What does the graph look like? Well, instead of going to 1, it goes to 2. It's just twice as tall. Instead of going to -1, it goes to -2, twice as tall. I'm mostly just looking for a sketch on this. I'm not going to be as hardcore on that, but verifying the h and the k, right, is going to make this graph a lot easier to do. So again, now what is our domain? Well, this time it changed. It moved, right? The domain, x goes left forever, x goes right forever, but where's the hole this time? At -1. So it goes from -infinity to -1, or -1 to infinity. And that's where the hole is. The range is not moved, so it's from -infinity to 0, or 0 to infinity. So they explained it a little differently, but what? Our domain matches, got shifted to the left one. The range was not shifted, so it stays the same. They want you to verify the vertical asymptote, the horizontal asymptote. We found all of this. Notice they don't use the not equal. That's just my thing I like to do. Graphing, again, I can use my calculator to do that, but that matches our overall sketch. Just what? Twice as tall. What do I do if it's not in the right form? So for instance, if it was well, we can still see the horizontal asymptote. We can still take that denominator and say x cannot equal, what was it? -1 this time? X plus 1 cannot be 0. Solving for that, x cannot equal -1. Okay? So I know that part. But what about the horizontal asymptote? Well, there's a couple ways to do this. One way, and this is why I had this at the initial notes, so we know that the x, or the vertical asymptote, is where the denominator cannot be 0. But for the horizontal asymptote a lot of people go, sweet, no number out here at 0. That's actually wrong this time because this is not in our ax minus h plus k. For this to be working, I need that number up here all by itself. So this is not in the right form. So this is where I like to think about the horizontal asymptote as x gets really big. Okay? So what happens if I take this equation and I put in an infinity plus 2 over an infinity plus 1. Again, this is not the only way to do it, but this is the type of thinking you will be doing in calculus, so I'm trying to prepare you for that. And here's my argument. If I had $9 million, would another $2 make a significant amount? Am I going to go, no, I have $9 million and 2? Some of you are like, yeah, $2 is a big deal. Okay, what if I had 90 billion? Right? Then you're like, $2 is like a percentage of what I have. It's absolutely insignificant. So when I put infinity, which is way bigger than 90 billion or 900 billion or really big numbers, right? Then this 2 and this 1 become insignificant. For all intents and purposes, if I have 900 billion and $2, it's basically like 900 billion. If I have 900 billion and $1, it's basically 900 billion. And then what you do is you simplify what's left so that infinity divided by infinity, y gets close to 1. Will it ever actually equal 1? No, because that 2 and that 1 will always keep it from getting there. But it will get really stinking close. And so that's one way. If I want the horizontal asymptote, I can think about it as x approaches infinity. You don't like that? That's okay. Then what you do is you take our equation, and you're going to need to do x plus 2 divided by x plus 1. You're going to turn it back into this form right here. We've done this before. X times what makes x? How about 1? Multiply and subtract. So x plus 1 becomes negative x minus 1. So that's the multiply and subtract. And what I'm left with is 1 as my remainder. So it's really 1 plus 1 over x plus 1. This is now in the same form as this. It's basically what? Y equals, I'm going to reorder it a little bit, 1 over x plus 1 plus 1. So that our h is negative 1. That gave us up here our vertical asymptote. And our k is positive 1. Gives us that. So you're either going to have to divide that out to get it back into, its kind of standard form, or you can think of x going towards infinity. But either way, we have a horizontal asymptote at 1. Okay? Again, the a is positive, so nothing else going on here very exciting, so I'm just going to kind of sketch it out. Nothing flipping. So this is just a sketch. If I want more exact, then what I could do is go to my calculator and go, what was it, x plus 2? Control divide, x plus 2 divided by x plus 1. Horizontal at 1, vertical at negative 1, which we said was the same thing as 1 over x plus 1 plus 1. And we got that using long division, and that's the same graph. Just two different ways of looking at the same exact graph. So let's see how we did through the topics here. Taking this, they go straight into the division. It goes in one time with one remainder. So then they say, well, hey, that's the same thing as 1 over x minus 1. So there's basically our H in our K form. I didn't do the domain and range. I should do that real quick. It's a good thing I checked these things. So our domain goes from negative infinity to positive infinity with a hole at -1. So negative infinity to -1, or -1 to positive infinity. And our range goes up and down forever, but has a hole at +1. So negative infinity to 1, or 1 to infinity. That now matches. Okay? Next, 1 over x squared is another type of rational, but it acts a little differently. So we're going to see how this one works. So again, this will be another parent graph. And then what we'll do is more complicated ones off of this. So if I did 1 over x squared, take the denominator, and it cannot be 0. Solving that by square rooting both sides, x cannot equal plus or minus 0. Okay? Or just 0 this time. So what that does, though, is that puts an asymptote right here. Where do I get the horizontal? Well, I mean, one big hint is nothing's been shifted, so it's probably still at 0. But if you weren't sure, this was our vertical asymptote. If you wanted the horizontal, and you weren't ever sure, just stick an infinity in there. 1 divided by infinity squared. What happens if I divide by things that are really big? Basically, y will get really close to 0. What do I mean by that? Well, if I take 1 and I divide it by 10, right? If I take 1 and I divide it by 1 and I divide it by 1,000, what's it doing? It's getting closer and closer to 0. And this just means, what, 6 decimal places before it gets there. What happens to 1 if I divide it by infinity? Basically just says it's pretty stinking close to 0. So y will never equal 0. Plugging in some points. 1, 2 gives us 1/4. 3 gives us 1/9. It's going to do the same thing here. And it's going to skyrocket again. Same thing on the left, but when I plug in -1, it doesn't go down to -1. Why? Because we squared it. So that -1 squared brings the graph back up here. So it's the same thing, just both on the top. So if you're not sure, plug in a couple points and find out the regions where this graph goes around this netting. We're going to have to be doing that a little bit anyway. But again, this is just an overall intro. What is our domain? X goes from what? Negative infinity to 0 with the hole there, or 0 to infinity. Our range is different this time because y does not go down forever. It goes up forever, but it goes down pretty close to 0. So from 0 to infinity. Doesn't have a bottom part. So let's see how we did through the example. That's the sketch we got. We can use our calculator to do that. Again, another vertical asymptote at 0. They don't have the horizontal on there yet. I don't know why. But going on. All right, so here's where we have 1 over x minus 1 squared. So what they've done is they've taken our parent graph and they've done a x minus h squared plus k. So it took our parent graph and it shifted it to the right one. So there will now be a vertical asymptote at x equals 1. really x cannot equal 1, the way I like it, okay? If you didn't see that, take the denominator, set it equal to 0. Solving it, x minus 1 equals 0, x equals 1. Where's the horizontal asymptote? Well, the k this time is 0. So that means y will not equal 0. If I know what the graph looks like, just like its parent, I can just sketch it and be done. If you're not sure, you need to check numbers. If you're not sure, and I'm not letting you use a calculator on the question, which might happen, then what you need to do is check numbers before and after any vertical asymptotes. So here we said x cannot equal 1. So I would just say, well, what happens if x equaled 2? Well, that would give me 1 over 2 minus 1 squared. 1 over 1 is 1. So at 2, it goes up here. That tells me it's in this region up here. That's to the right of that. What if I check to the left of that? So instead of 1, let's just check what happens if x equals 0. Well, that would be 1 over 0 minus 1 squared. That gives me 1 over 1. That also gives me 1. So at 0, it crosses right there at 0, 1. Tells me I'm in the top region on both sides. Not my favorite way, but if you can't remember what the parent graph looks like, then you can just kind of plot some points and figure out what region is this netting in. The fact that it's squared makes it both up. But if you forget that, you can always check points before and after any vertical asymptotes to kind of figure out the shape in the graph. How do we do? Shifted over 1. Domain range. Domain was negative infinity to 1. I probably should write that down. So our domain on this time the hole's at 1, so negative infinity to 1, or 1 to infinity. Our range is different because it doesn't go down forever. It just goes from 0 to infinity. So we talked about domain and range. We talked about the shifting. What if, there's our graph, this one has several pieces? Well, no big deal. It just has an h and a k. So 1 over x plus 2 squared minus 1. Our h is going to be opposite, negative 2. Our k is going to be negative 1. So shift the x to negative 2. Shift the k to negative 1. X cannot be negative 2. Y cannot be negative 1. The a is positive, so this will look just like its parent graph. Our domain, from negative infinity to negative 2, or negative 2 to infinity. Our range, how about, goes down to negative 1. So negative 1 to infinity. How would this example be different if all I did was a negative 1 on the top? Right? Well, we have the same netting. We have the same negative 2, negative 1, right? But if our a were a negative 1, then all it would do is take the graph and reflect it. So it'd be the same graph, just reflected. Our domain here would be the same. So negative infinity, negative 2, or negative 2 to infinity. But our range would be different because now it goes downward. So it would actually go from negative infinity to the negative 1. Let's go ahead and double check this real quick in the calculator. So where are we at? Let's see. 1 over x plus 2 squared minus 1. Is that what we thought? Down 1, negative 2. That's what we got on this one, right? And then we said, what if I change that top from a 1 to a negative 1? All it does is reflect it downward. See how we did? Saw that. You've not seen this one yet. Okay, so this one's going to be a little crazier. So 2x squared over x squared minus 4. Going to be kind of the hardest ones we're going to see because it doesn't fit any of our previous ones. Let's just start with taking that denominator and saying it cannot be 0, right? So what happens here is we get x squared cannot equal, we move the 4 over, so 4. But when we square root it, what we get is x cannot equal plus or minus 2. We get 2 vertical asymptotes. We get that x cannot equal 2, and x cannot equal negative 2. So this creates 3 different regions, okay? How do I get a horizontal asymptote? Well, I mean, I can try to divide it and do an h and a k, but it really, to me, it's more complicated than it's worth. What I like to do is this. To get the horizontal asymptote, I say what happens as x approaches infinity. Okay? So what we end up with is, and all I do is I take anywhere there's an x in the equation and I put in an infinity in its place. So I get 2 times infinity squared over infinity squared minus 4. And I get rid of the insignificance. What do I mean by that? If I have $90 billion squared, that minus 4 is insignificant. Why didn't I cross out the 2 this time? Because somebody's saying, well, no, that's a big deal. If I got $90 billion and somebody else has 2 times that amount, that's still important. So we get rid of the adding and subtracting, but the actual multiplying we keep. And so once I've gotten rid of kind of the insignificant adding and subtracting, I reduce what's left. The infinities cancel. And so y will get really close to, but never equal 2. Let me kind of show you algebraically what I'm doing here, okay? So 2 infinity squared infinity minus 4. Right? So what I'm saying here, let's see if I can clear this. All right. If I take 2 times some number squared divided by, and what was the bottom one, infinity squared? Minus 2 minus 4. This will not equal 2, but we're saying that once I square that 10 and square that 10, it's going to get pretty close to 2. It's not exact. But what if I took that and changed that 10 to 100? Or I'll kick it up, so change it to 1,000. Then it's still going to get closer and closer to, but never quite reach 2. right? This 4 became really insignificant. It's that little 0.00001 right there. That's the 4. And so what happens as this gets towards infinity, is that the subtracting doesn't matter, then the infinities cancel, and this gets really close to, the calculator's not going to handle this, it's too close. Let's try this. So I'm going to simulate infinity by putting in a big number. Let's see, 1, 2, 3, 4, 5, 6, 7. All right, 1, 2, 3, 4, 5, 6, 8, 9, 10. 3, 4, 5, 6, 7, 8, 9, 10 squared minus 4. Really close to 2. Okay? That 4 is insignificant. That 2 matters. Okay? You still have twice as much. So what that does is it gives me an asymptote at y cannot equal 2. So what happens in this netting? Short answer is, I don't know. Depending on the situation, these can go a couple different ways. Okay? So when I have, I'll do it this way. When I have this netting on the left and the right and horizontal, I can have where one is down, the other is down, and then generally what happens is the middle goes up. Or I can have if these both are going upward, then generally this goes downward. Or I can have if this one goes upward and this one goes downward, then what it does is this weird like cubic thing in the middle. So there's a lot of weird options for this. And the only reason I know that kind of these are the things that generally happen is because I've done these a lot. So how do I know what the graph is going to do if I can't just graph it in my calculator? This is what we talked about before. I check numbers on each side of our vertical asymptotes. Okay, so this had a vertical at -2. So I'm going to check what happens if x is -3. I plug it into the calculator. And I don't even need an exact on this, but I'll get kind of approximately, what is that, 18 over 5? So 3.6. What does that tell me? Well, it's somewhere up here. That tells me that we are in this region. If I check past 2, I would check something like x equals 3. Two times 3 squared, 3 squared minus 4, again 18 over 5, 3.6. That tells me this is up here. So from my experience, I think this is going to be down like this. But let's check. Check here in the middle. Check -1 and +1. 2 times -1 squared, -1 squared minus 4. That gives me 2 over -3, -2/3. Not a great number, but it's just down kind of here. Check it at +1. 2, 1 squared 1 squared minus 4 will give me 2 over negative 3, or negative 2/3. That's the same. This is where I'm going to have this kind of parabola in the middle. And if you're not sure, check 0. And you get 2 times 0 squared. 0 squared minus 4, get 0. This graph crosses right here. So it creates kind of a parabola shape in the middle. How do I know that? Check points till you kind of figure out the region. If they're both up, the parabola in the middle is down. If they're both down, the parabola in the middle is up. If they're opposite, you get like this little cubic S in the middle. But if you're not sure, plot some points. Okay? So that's it for our first section. Only a few sections for chapter 5, so let's get to work on that.